we now come to a new law of nature. Oersted showed us that electricity can be a source of magnetism, and so the question naturally arose, can magnetism be a source of electricity? You will never read of the name William Jenkin in any textbook on physics or science. Nevertheless, Michael Faraday said that although many colleagues had offered suggestions and observations for him to follow up on, only one proved useful, and that was the suggestion and the observation of William Jenkin, who discovered a new way to get shocked. What he did was, as illustrated here, is connect a couple of wires to a battery. But the wires, in turn had loops in them. There was a section of the wires that consisted of several loops. We would call this an inductor nowadays. And so he cheerfully connected the wires to the battery. And so there was electrical current then, charge flowing through the loops of wire. When Mr. Jenkins, however, removed the wires from the battery while maintaining a firm grip on the wires, he received an electrical shock. Faraday first thought that this indicated a kind of inertia of the electricity, so that once the battery had set the electricity into motion, the removal of the battery did not immediately stop the current, but the current continued to flow for a while by inertia through the body of Mr. Jenkin. Indeed, a similar effect occurs with water moving through a pipe when a valve is suddenly closed. The momentum of the water behind the valve can actually often can be heard as a thump and can even break the pipe itself. This water hammer effect, however, differs from the Jenkin effect in a couple of important aspects. The water hammer effect only depends on the amount of water and the velocity of the water through the pipe, its initial velocity before it is suddenly stopped. It does not matter whether the pipe is in loops, for example. It just matters what's the total amount of water there. Whether the pipe is straight or looped has no effect. Also, objects outside of the pipe do not affect the water effect. So, in the case of the Jenkin effect, however, loops of wire, like here, you take this single wire and loop it, that increases. It can increase the shock greatly. And if there's iron nearby, for example, and particularly inside of the loop itself, although the iron does not penetrate the wire, the iron, again, can greatly enhance the experience. Decades later, Maxwell picked up this thought, and noting these differences between the water hammer and the Jenkin effect, suppose that, well, maybe there is in fact inertia, but the inertia is due not to the motion of the electricity, but rather to the motion of something in the space surrounding the wire. And what surrounds the wire? As Oersted taught us, magnetism. Maxwell supposed that the magnetic field lines can not only deflect north and south poles, but also rotate and carry angular momentum. Here's a cross-section of one of his diagrams. The hexagons represent, in fact, cross-sections of the magnetic field lines, and the little circles represent the particles of electricity, which both can set the rotation of the magnetic field lines into existence, and can also, since being sort of idler gears, could also allow adjacent field lines to rotate in the same direction without friction. I like to think of these, the rotating magnetic field lines are sort of like spaghetti gears. So strands of spaghetti in space all rotating about their axis, closed in on themselves and carrying angular momentum. When the electrical current, represented by the little idler gears, is set into motion, the idler gears grab upon gears in the magnetic field lines and set them also into motion. And it is in the field lines, the rotating field lines, that the momentum resides. And those field lines do not wish to cease from rotation, but rather their inertia will drive the electric particles of electricity, those idler gears, into motion, or continue keeping them into motion should they try to stop. In this way, Maxwell introduced the dynamical concepts of inertia and momentum into the space surrounding the wires. It's sort of like this, the rack and pinion mechanism. The rack here is moving. It's setting the pinion into motion. But if the pinion is massive, and the rack should try to stop, the pinion will continue, or will tend to continue to keep rotating, and thus will oppose any force that is trying to stop the motion of the rack. In this view, the rack represents the electricity. The motion of the rack represents the electric current, and the inertia and momentum of the pinion represents a kind of inertia due to the rotating field lines of magnetism surrounding the wire. It is only when the motion of the magnetic field lines is disturbed that you sense, via, say, an electric shock, just how much momentum is stored in those rotating magnetic field lines. Here it is set out in words, written words for your consideration. We can now understand why having successive wraps of wire matters. The superposition principle, when applied to two turns of wire, enhances the magnetic field lines and thus enhances the momentum carried by those field lines. Each turn of the wire increases the momentum that is stored in the magnetic field. We'll replace the multitude of rotating magnetic field lines with a single gear. Here, the switch is open, so neither the gears of electricity in the wire nor the gears in the magnetic field, represented by that single large gear, are in motion. Nothing is moving at this time. When the switch is closed, the battery can now exert an electromotive force in the clockwise direction, in this case, on the electricity. The field, as it builds, owing to the third law of motion, pushes back on the electricity in the opposite direction. So the battery pushes on the magnetic field, causing it to rotate in the clockwise direction. And the reaction to the battery's electromotive force is the electromotive force due to the field. When the switch is open, the momentum of the magnetic fields is stopped, and so the directions of the electromotive forces both reverse. It is the electromotive force of the battery acting in the counterclockwise direction that shocked the unfortunate Mr. Jenkins. Since the electric current is to a good approximation proportional to the electromotive force, we may measure the electromotive impulse delivered in the Jenkins effect the same way we measure charge passing through the wire in the case of the Weber-Kohlrausch experiment. We can use a ballistic galvanometer. In this measurement, the momentum of the field, the magnetic field, instead of shocking the unfortunate Mr. Jenkins, delivers its impulse to the needle. Once the field is gone, of course, the impulse is gone. So the needle simply goes to some maximum deflection and then goes back to zero. Its maximum deflection is a measure, a detection of the momentum change of the magnetic field. Experiment shows that the change in magnetic momentum is proportional to the electromotive force impulse. For example, in an experiment, each additional turn of the wire increases the impulse delivered to the galvanometer by a proportional amount. Nowadays, we in fact define the magnetic field primarily by this induction of EMF. And so we just simply set the change in the flux or electrokinetic momentum is equal to the EMF times the time interval over which the EMF acts. This is strictly analogous to the change in momentum equaling the force times delta T in ordinary mechanics. We could define this unit of magnetic flux in electrostatic system of units if we choose, or we could choose an electromagnetic unit to describe this the magnetic field. In fact, the Gauss is based on it is an EMU unit that is still in use. You will frequently, especially geophysicists and astronomers, like to use the Gauss as the unit of magnetic field flux. Nowadays, people like to use meters and kilograms to define their system of units. So the SI unit of magnetic induction flux is the Weber. As it says here, the Weber is the magnetic flux, which, if it's linking a circuit of one turn, would produce in it an electromotive force of 1 volt if the magnetic flux, were reduced to zero at a uniform rate in 1 second. As in the case of electrostatics, we define the magnetic field as the flux density. Thus, 1 Tesla is 1 Weber per square meter. Here's a problem based on this definition of flux. If you stop the video, you can study the way this calculation was done. If you have a hoop that's intersecting 65.5 Webers of magnetic induction flux, flipping that hoop effectively reverses the momentum relative to the wire. And so the change in flux upon the flipping of the hoop is twice 65.5. Just like in the case of mechanical momentum, the direction matters, though now the direction is more a kind of circular or rotational direction rather than a linear direction. This source of Mr. Jenkins' pain is now called self-inductance. And since the magnetic field is strictly proportional to current, in fact, the magnetic flux passing through, in other words, the number of magnetic field lines passing through the hoops of a circuit like shown here, is strictly proportional to the current. And so the proportionality constant we call the self-inductance of the circuit element. The unit of self-inductance is simply the EMF impulse, which is a volt second, divided by the unit of current, which is the ampere or coulomb per second in SI units. We call this the Henry in honor of an American physicist. If a battery or some other EMF external to the inductor changes the current at the rate of 1 ampere per second, the momentum, the inertia of the magnetic induction is 1 volt contrary to whatever EMF is causing the change in current. The self-inductance of a circuit element is exactly analogous to the rotational inertia. If the form or shape of the inductor cannot change, then it is particularly easy to do the mathematics involved. It is exactly analogous to F equals ma. If you suddenly apply a force to an object like a baseball that has some inertia, the velocity of that baseball increases at a constant rate. Its velocity increases at a constant rate, constant acceleration. In the same way, exactly the same way, and for the same mechanical reasons, if you suddenly expose an inductor to, say, 10 volts of constant EMF by closing that circuit, the current in the circuit, in the absence of resistance, increases at a uniform rate as shown in the graph D.